Um, In this one, we'll study wave motion. We'll start wave motion here. Can someone try? What is wave motion? Yeah, what is wave motion? What do you mean by wave at least? No one? Are you present? Shamhita?
Yes, sir.
And Mook?
Yes, sir.
Okay. Now, wave means like it's just a disturbance from a particle or like means like it's disturbing from moving from one point to another point in form of wave or disturbance which is moving from one point to another point like in form of wave. So wave motion is that motion is called wave motion. In whatever motion it is moving, as we are drawing, generally we are drawing this way. But it's not just this, can be this also. That's what we are going to see today. In which this is what? It's like a disturbance travels from one point to another point. Okay. So disturbance is traveling. See, understand this disturbance and particle. Difference between disturbance and particle. Disturbance means like that motion is disturbed there, but particle is not moving. Now, this wave is here. Okay, I'm taking this particle. So particle is there, but this disturbance, this is called disturbance. It's moving here and that disturbance. This disturbance has like, if I draw particle here, this particle is in same position, but Disturbance is changed here. It moved here. So in short, this is just up and down movement. There is no wave which is traveling like this. There is nothing like traveling that way. Okay, this as we are seeing this one, that we are seeing this wave. Actually, this is nothing traveling this way. It's not traveling in like this direction. Only this particle is here. The wave is coming here. Then another particle is here. Another particle. There are so many particles. But if you observe only one particle here, wave. So then due to particle here, then wave is here. This point. Then this point, wave, the same particle, if it is here, this is different. The same particle is here, it's an upward disturbance. This is downward disturbance. So disturbance is going up and down. Particle is in the same position. Particle is not moving. We are just studying about wave motion. So disturbance is moving. Wave means disturbance is moving. Particle is not moving. Particle is in same position. So let's write here. From disturbance travels from one point to another point. Let's add this one also. But particles of medium do not travel from one point to another. Okay. So here we saw disturbances traveling. Fine. Now disturbance, there are two ways of traveling these waves. Okay, one mechanical and another one non-mechanical. And one more thing we need to keep in mind, these things also require energy to propagate. Propagate in the sense like movement. So two types of wave. Mechanical wave. Second one, electromagnetic or non-mechanical. In this one, see, mechanical waves, it requires medium. Medium to propagate. Here, does not require to. Now, when it requires medium to propagate, so okay, now tell me which are things which energy required medium. Do light energy require medium? Yes or no?
No, sir.
What about sound? Right now you're speaking. So, does sound energy require medium?
Yes, sir.
So, sound energy will come under mechanical wave. Example, sound wave. Yeah, example, light. Light wave in the sense UV rays or X-rays also. All those waves, like all those electromagnetic waves. Light waves means UV rays, X-rays, gamma rays, radio wave. Those all waves does not require any medium for travel. But they have their own different properties. That's what we are not going to discuss right now. Okay. So let's start with the first one, mechanical. In mechanical also, there are two ways. There is transverse wave, longitudinal, longitudinal wave. Now, by the name, can you understand what will be this one? Can you guess what you mean by transverse? What is transverse wave? Do you know translatory motion? No? It's
So
actually linear
something
motion,
it is like linear motion which goes in a straight line.
straight path. This is also similar. So in this one, it moves this direction. See, actually both longitudinal and transverse both moves in this direction only, but there are small changes here. So transverse wave in this particle oscillates in direction perpendicular of wave motion or propagation. So I can draw like this here. So this is the wave motion. So around this, it is propagating like this. See, it is moving like this. So that example, like ripples of that water, if you throw a stone, it will ripple there. Then like a string, when you're playing guitar, that string will move up and down. It vibrates. Those are the waves. So this is the crest. This is trot from this point to this point, or this crest to next crest, or trot to next trot. There is one wavelength I'll draw here. I'll draw 0 to 0. It is wavelength lambda. Okay, and remember one thing, it is very, very important that it travels only in solid and liquid. Then only it will give you crest and trot. But let's write about this guy, longitudinal. So particle of medium oscillate their position about their mean position. So example, sound wave. Here example, what example I gave? Ripple and stream. Two example I gave, right? Okay. Here, sound wave or spring. The motion produced by the spring, there is also a longitudinal wave. So if I take a spring and if I connect in this solid space here, if I stretch it here, so this is your compression, this is your rarefaction. This is a compression, then there is rarefaction. Compression and rarefaction. This can travel through all the mediums. Liquid, solid, and solid. Done writing part?
Yes, sir.
Okay. What about others? Chalo, next. We have little time. Okay. Equation of progressive wave. From name, you can understand progressive. That means a traveling. So we will assume that this is traveling along x axis. So if it's traveling along x axis, y equals to a sine omega t minus kx. Y is the displacement, x is the location or point, time t, a is the amplitude. What else? Yeah. So omega we can write here a sine 2 pi by t by t. I'm writing directly. Minus x by lambda. Equals to a sine 2 pi by lambda. See how I'm writing this one? I'm writing directly here. Wait. Vt minus x. See, these are things like v equals to into lambda. So this your frequency. This is frequency. Wavelength. Okay, then omega also we excuse me, 2 pi by t lambda. What are these things? It is angular wave number. This is angular frequency. Anything else left? Everything we wrote? Actually, this is your standard formula. We will use this one. or this one. This is not required. V by lambda will be frequency. Yeah. Frequency means 1 by T. From here, frequency 1 by T. And V equals to lambda here. I hope you understood what I directly wrote. Are you able to understand, guys?
Yes, sir.
Okay. Aditi, Samhita, what about you both? Are you able to understand the substitution? Now, suppose this wave is traveling in negative direction. If negative direction, then this equation will become y equals to a sine. I'm directly writing this one, not for the first one. 2 pi t by t minus x by lambda. So it will become t by t plus x by lambda. So you can guess here, it will be what? A sine omega t plus kx. Instead of minus, it will become plus if it is moving in negative direction.
Sir, could you want to scroll up? So what is small t divided by big T?
This capital T is the time period, and small t is the time for that particle where it is moving. So this we got it from omega. Omega equals to 2 pi by t. See all this conversion I wrote here. Done this one? And doubt?
No, sir.